I need to turn my microphone on. Yeah, so increased dispersion forces means increased forces of attraction. Increased forces of attraction means the molecules want to be closer together. And so because they want to be closer together, it requires more energy to separate them.
And a question about this, what would
you always have to include the type of intermolecular force, what's changing that makes it greater. So like why is butane greater than methane? And then you have to have something that explains because the force of attraction is greater, that this means that it'll take more energy to separate. So basically, what is a boiling point? A boiling point is the temperature at which the liquid will turn into a gas, which means the particles separate. All right, hold on. We are about to move on. I'm giving about 20 more seconds for those who are still writing. You want a staring contest with this? Your poor eyes.
I can win.
All right, here we go. Next question. Take a look at this one. This is another textbook question, but it's important because it highlights the types of questions that can be asked on paper 2. I see so many paper 2s where this type of question is asked. Last year, June 2023, my students that tested, it was crazy. This topic didn't show up at all on version 1, which is the version that we took. Version 2 had tons of questions about intermolecular forces. So you never know which version you're going to get, so you have to study for everything. But this is a very common type of question. Let's take a look at it. Bromine, Br2, and iodine monochloride, ICl, have the same number of electrons. This information freely told to you. But the boiling point of iodine monochloride is nearly 40 degrees Celsius. So they're telling you that ICl has a higher boiling point, right? They're saying this is a higher boiling point than this by 40 degrees. And the reason why, well, that's for you to decide. Let's explain the difference in boiling points. So what was he looking at here? They got the same number of electrons. What would they be looking at? Yes. Yes. Absolutely. So the first thing you should analyze when you are making a comparison is type of IMF. Take a look. What is the type of IMF for Br2? It's a bromine connected to another bromine, so did it kick me out? I'm going to keep the annotation. Oh, what type? Well, I see what happened. You can see what happened. It says I lost my network connection.
Because they're the same.
Dispersion is correct. Hold on. So Br2 is dispersion. Sometimes the internet is wonky. I'm disconnecting and reconnecting. The same thing I tell y'all to do when it tells me, when y'all ask me, hey, my internet's down. I'm doing all of those things.
Yeah, I did like that. I guess
Only outside.
If we're supposed to work takes too long, I would say last year's recorded lesson. I record every year.
Then what about the ants, though?
So it looks like it's working now. By the way, that's true. Every time that my thing messes up and the internet cuts out completely, I recorded the lessons last year and the year before. So like I can literally just take a lesson from last year and post it up for most lessons. So if I I am prepared for a lot.
Thank you.
So if worst comes to worst, but I always try to get it to run first because I'd rather it be the lesson from this year because sometimes we start finishing slightly different places. All right, here we go. Let's continue. Type of IMF. Julio was completely correct on BR2. BR2 is dispersion, right? It's a bromine with another bromine. It's completely nonpolar. It will be dispersion. What's ICL? What is the intermolecular force? Because remember, boiling means separating molecules from each other, so it has to be intermolecular forces. What? Permanent dipole-dipole, correct. Right. Team is absolutely correct here. So because ICL is polar and without numbers, you just have to make that decision based on two different elements. So iodine is a different element than chlorine, so they have different polarities. They have different polarities, so that means that one's going to be more electronegative than the other, and so it's permanent dipole-dipole. Here's the deal. When we talk about boiling, we are once again talking about separating, in this case, molecules. So you have to have an intrinsic understanding that boiling means that you're taking particles that are attracted to each other in the liquid phase and you're literally separating them apart completely. Because gas particles, and we're going to get into that in the last lesson next class, is talking about moving randomly and rapidly. Gases move all over the place. There's tons of gas in this room. It's not really linked together. They don't stick together. They move all apart, right? So that's the idea. We're separating molecules. And so the comparison's here. Only if the type of intermolecular force is the same, then you would compare electrons in the contact points. But because the intermolecular force is different, well, that's the explanation you need to give. So in terms of explaining, to get the marks, what do we now need to say? BR2 has, you could say dipole-induced dipole, or induced dipoles, or temporary dipole, or you could say has dispersion forces. My favorite. Dispersion forces, there's so many synonyms, which are weaker than the forces in ICL, which are I would say forces for ICL, which are dipole-dipole or permanent dipole-dipole. Because the force is stronger in ICL, this means that the boiling point must be higher. That's the second mark. So the second mark is to say because or since the forces of attraction is greater in ICL, it will require more energy. To separate the molecules. So you can see the key points are getting hit here. One of them is to talk about the type of intermolecular forces being different, and the second is to state again that the stronger the force of attraction, the more energy is required to break apart that force of attraction. And boiling itself is the process of changing a liquid to a gas, which is separating molecules. So that's the idea of what you need to hold on to here. So I'm going to give some time. Yes?
Could I also draw the Lewis structure to also determine?
You can draw the structures. But if they say explain, that means the command is words.
I'm saying like draw the Lewis structure to determine based on the force.
BR2? You can draw the Lewis structure to determine the force, yes. Yes. Bathroom? Yes. Yes, Hakeem.
It has a higher boiling point
because it has a stronger force of attraction. So because it's a stronger force of attraction, it requires more energy to separate. More energy is reflected by a higher temperature, which is a higher boiling point.
So in that case, only the principle something like phosphorus hydrogen
Okay.
would be
pH 3.
pH 3 more or less would have a higher boiling point than ICL, right?
I don't know. Depends on the difference in their dipoles. Like, it depends on the difference in their electronegativities. So, not exactly, no. The higher the dipole difference, though, the greater. So, like, hydrogen bonding would have a higher boiling point. Because hydrogen bonding, we can say for sure, is a greater dipole. But I can't say the difference in P and H is greater than the difference in I and Cl. Because phosphorus is not really that electronegative. So, you have to have the numbers to make that decision. All right, here we go. So, boiling point, hydrogen bonding. If you have something that hydrogen bonds, it has a higher boiling point than other types of permanent dipole. So this gives water its properties of insulation, meaning that it requires a lot more energy than you would expect for water being such a small molecule to boil it. Case in point, water's boiling point, does anybody know it off the top of their head? 100 degrees Celsius, which in American speak, Fahrenheit is 212 degrees Fahrenheit. 100 degrees Celsius is the boiling point of water. And so other molecules of a similar molar mass, let's take a look at one real quick. I'm just going to pull it off the screen. Let's see. H2S is heavier than water, has more electrons, right? Sulfur has more electrons than oxygen, do you agree? The boiling point of water is 100 degrees Celsius. The boiling point of hydrogen sulfide is negative. Water, being smaller, less electrons, has a way higher boiling point. And so the explanation of why is hydrogen bonding. So because of the special stronger dipoles between water, this gives water a much higher than expected boiling point to similar molecules. So if you have a question where you're being asked to compare, so if you are asked to compare boiling points or melting points, and you see H with F, O, or N, why will the molecule which with H and F or H and O or H and N have the way higher boiling point? The answer is the answer of why the melting point boiling point is so much higher.
Wait, so what's the order of more, the strongest to least strong in affecting the boiling point? First is hydrogen bonding.
Yeah. So
Then
for
it's-
molecules.
Right.
So for molecules, the order, I'll write it for you now. The general order is H bonding, then permanent dipole, then dispersion force. So H bonding is always going to have the highest boiling point and melting point. Then it's going to be permanent dipole. Finally, it's going to be dispersion are weak. So you may want to write that down. This is the order, like that. Yes, if you are asked to compare the boiling points or melting points, you see H can combine with F, O, or N in a molecule. The reason why its boiling point is going to be so much higher is because it has hydrogen bonding capabilities. And what does that even mean again? What is the hydrogen bond from last class? What does that even mean? It means there's a big difference in electronegativity, right? Big difference in electronegativity equals extra strong attraction. And so that's why it's hydrogen connected to one of the three most electronegative elements, because it gives you the biggest difference in electronegativity, which gives you the strongest overall attraction. And so stronger attraction means it requires more energy to boil than you would expect. So I'm going to leave this up for a bit and then we'll continue. There's some other special properties we have to look at. You may want to take a picture because I'm going to move forward shortly. All right, are we good? Moving forward. So here we go. You have been given a table. You've got some group 5 halides. You've got some group 5 hydrides. Not halides, that's hydrides. It's the first year I ever called them. I think. Hydrides, not halides. Halides would be group 17. Those are all with hydrogen. So it says NH3, PH3, ASH3, and SBH3. And you are told to explain the trend. So what is the overall trend? What's the overall trend here? Negative 33, negative 88, negative 55, negative 17. At least from here to here, what's happening? It says from phosphine, that's increasing.
Yeah, wait.
How can we be sure? Well, let's make a number line. Put the number 0 there. You've got negative 88, negative 55, and negative 17. Just for yourself. I taught you this, in the past. If you get confused with positives and negatives, it always helps to make a number line. Make a number line. From negative 88 to negative 17, this is an increase in boiling point, which I'm going to do BP for boiling point. So explain the trend. What is the difference between phosphorus to arsenic to antimony? Yeah, it's antimony. What is the difference? What would be the cause? They all have the same shape, don't they? Because they are elements in the same group, so they have the same amount of valence electrons. So if you drew them, they would all look the same. They will have the same shape. They would have the same structure. They would all be permanent dipoles, I guess? Yes. Leave it at electrons and you're correct. So the trend in boiling point, the only difference between these three elements is the amount of electrons. So the amount of electrons increases, total electrons, not valence electrons. But remember, for dispersion forces, we spent a long time about last class saying, all we look at at dispersion forces is amount of electrons. So the amount of total electrons increases, which increases the dispersion forces. So it will require more energy. More energy to boil. Or to separate the molecules. So that again. Remember, increased boiling point is increased energy to separate molecules. That's what we're talking about when we talk about increased boiling point. And so then the second part says, well, what about ammonia? NH3. That's the smallest of them all. It has the least amount of electrons. Why is the boiling point higher than expected? So So remember, this is NH3, right? So it's higher than expected. It's not the highest of them, but it's much higher than expected. It should be lower than -88, right? But it is because, absolutely, because hydrogen bonding. And so, due to hydrogen bonding, ammonia has a higher boiling point. And we can leave it at that. Due to hydrogen bonding. So you're pointing out what's the difference. Hydrogen bonding is a stronger force of attraction. Stronger force of attraction means there will be a higher boiling point. And so that's checkup 13 from the textbook. Let's see how close we are to done with this first part. Yes, question? Go ahead.
So wouldn't hydrogen bonding also apply to the other?
No. Because in order to exhibit hydrogen bonding, hydrogen has to be connected to chlorine, oxygen, or nitrogen, one of the three most electronegative elements to give the biggest difference in electronegativity, which gives the extra polarity. Okay, we're going to go ahead and continue now. So the next topic is going to be pretty quick, but we're going to go back to it as we keep going through the lesson. States of matter. Our final lesson is talking about gases, but we do need to be aware of general states of matter. In pre-ACE or honors chemistry, I actually asked you to memorize a bunch of states of matter for elements. I told you to memorize that metals were always solid except for mercury at room temperature. That these ones over here in red are all gases. By the way, this periodic table kind of spoils it. Like if you can see it. These are all your gases. And liquids are only mercury and bromine. So here's the deal. The standard states are at room temperature and pressure. So standard states, room temperature and pressure, means that you need to memorize the physical state of matter for elements and compounds at room temperature. The state of matter is affected directly by the intermolecular force. A weaker intermolecular force favors what state of matter? What do you think? So if you think about it, I told you to memorize F2 was a gas. Well, isn't that only 2 atoms and with a low amount of electrons? F2 is a gas. Take a look. Cl2 is a gas as well. But Br2 is a liquid and I2 is a... So what's happening? More electrons is affecting the state of matter. So it actually turns out that the greater the intermolecular force, the more likely you have a solid or a liquid. The weaker the intermolecular force, the more likely you have a gas. So that funnels into the states of matter that you're asked to memorize for the different elements. We're going to talk about pure metals in a little bit. That's at the beginning of the second part of the lesson. But pure metals all have a strong type of bonding. It's called metallic bonding, and that's why they're all solids. All right, so you need to memorize. Don't memorize. Ionic compounds at room temperature and pressure, so like table salt, is always a solid. It takes hundreds of degrees to melt table salt. Can we do it? Sure we can. Just need a hot enough burner to do so. But 25 degrees Celsius, which is a little bit warmer than the temperature of this room, about 77 degrees in American speak Fahrenheit. So that is what's considered to be room temperature, 25 degrees Celsius. Metals are solids, except for mercury. So when you see copper, when you see iron, when you see any metal, that's going to show up as a solid at room temperature. And then covalent compounds, well, are complicated, right? So the best way to see this is it's complicated. Why? What's the state of matter for carbon monoxide? Gas. Carbon dioxide. Water. Sugar. They're all covalent compounds, which means there's a wide variation in the state of matter for covalent compounds. They're usually liquids or gases. What would make sugar a solid, though? Why is sugar a solid? What do you think? You want to see a jump scare? Chemistry jump scare. Or biology jump scare, no matter how you want to look at it. Let's take a look at the structure of sucrose. That's table sugar. Structure of sucrose. This is sucrose. I'm pulling it up. Just to throw it out there. We said this is a solid, right? We know sugar is a solid. This is hopefully I picked the right one. Here we go. So this is some table sugar. You know, the type that you put in your coffee or Kool-Aid. Some good old table sugar. Why would you propose that this is a solid? What's going on here that makes it favor the solid phase? What do you think? So we said that carbon monoxide was gas, carbon dioxide was gas, water is a liquid. What's up with this? You see an OH there? Does this hydrogen bond? Does this hydrogen bond? Does that hydrogen bond? Does that hydrogen bond? That's a lot of hydrogen bonding going on. The more hydrogen bonds, the stronger the attractive forces. The stronger the attractive forces, the more likely it's going to be a solid. So you can analyze a larger molecule. Also, medicines and drugs typically are solids, unless they crush them in pulp form or liquid form, but they can be solids because they are larger and there's a lot more of those forces taking place. So I want you to draw trends here, not memorize exacts. Covalent compounds are complicated, but the idea is that the stronger the IMF, the more condensed the phase, or the more attractive forces, the more likely a liquid or a solid. So going back to carbon dioxide, what type of force is here? What type of intermolecular force is there? Friction. And we know carbon dioxide is a gas. So that's the way you have to think when you think of intermolecular forces. The stronger the intermolecular forces, the more likely you're going to have a liquid or solid. The weaker the intermolecular forces, the more likely you're going to have a gas. That does not mean that all dispersion forces are gases. What would be factors that influence it? You have to look at the amount of electrons. You have to look at the amount of contact points to favor what it's going to be. But you have to understand the trends in this class. You're not going to be asked, oh, pentane, what's its state of matter? But you could be asked, pentane or decane, which one has a higher boiling point? Or which one has a higher melting point? And then you'd have to count your electrons and contact points to figure that out. You have to draw trends here. All right. Ionic compounds are held together by much stronger attractions than covalent compounds. Why are ionic compounds always solids, whereas covalent compounds could be liquid, solid, or gas? What do you think? So like sodium chloride, solid. Calcium carbonate, solid. Ammonium chloride, solid. I can pick up any ionic compound and go to my, cabinets and be like solid, 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 solid. Why are all ionic compounds solid, but only some covalents? So they have fully positive and fully negative. So it's always charge, which means that strong attraction. Which means higher melting point and boiling point. So that's what you got to draw a conclusion about here. So ionic compounds are always going to have a higher melting point and boiling point than most covalent compounds, unless you had a covalent compound that had a really, really large amount of intermolecular force. It had to be really large, like maybe even a protein, or large protein, yes. Yes. Higher melting point, boiling point, strong attraction. The next thing we have to look at for intermolecular forces is solubility. Anybody know what solubility is before we talk about it? Right. So when we talk about solubility in this class, we're going to talk about solubility in water. There are other forms of solubility, but we pretty much focus on aqueous solutions. So the question is, will it dissolve in water? If I throw it in water, will it dissolve? And you can actually predict this based on forces of attraction. Water is polar, right? Water is polar, which means it has a partially negatively charged end and a partially positively charged end. And by bending water today, we're going to prove that it is polar because it has charge. The whole idea of what will dissolve in water is something else that has charges. So it requires something else that has charges. Something else must have charges to dissolve. And what do I mean by that? Well, do ionic compounds have charges? Sodium +1, chlorine -1. Are those charges? Yeah. So because they have charges, that means water molecules are going to be attracted to the positive sodium and the negative chlorine. So ionic compounds have charges, so they will be soluble in water. I can take salt, throw it in water, dissolve it, it'll happen. The other type of thing that will be soluble in water are polar molecules, because polar molecules have positive ends, negative ends. And because of those positive and negative ends, water is going to surround polar molecules. So is sugar soluble in water? Going back to sucrose? Yes. All of those O's and H's, right? Means it's very, very polar. It's going to be completely soluble in water. The solubility of sugar in water is crazy. In pre-Ex Chem last year, I did give you all something with solubility at the end of the year, like in the next to last unit, and you had a graph. And sugar is like 340 grams of it dissolves in 100 grams of water. Like, it's super soluble in water. And that's why soda, they put a lot of sugar in there. That's how they can get so many scoops of sugar in soda. I don't know if you've ever seen it. It's like a lot of sugars in soda. They've actually reduced the amount because people complained how it was really bad for our diet. But it used to be like 40 spoons in like a 16-ounce bottle. It used to be a crazy amount. All right, so water's polar. Anything polar or ionic will dissolve in water. So what about nonpolar? Will nonpolar things dissolve in water? It won't. So the way you think of it, so nonpolar molecules do not dissolve in water. Which makes sense if you think about a couple examples. Oil is nonpolar. So oil will not dissolve in water. Gases like carbon dioxide, do they dissolve in water? If you see soda, carbon dioxide bubbles are in there. Are they actually dissolved in water, or when you open the container, they come right out? They come right out because they're not actually going to dissolve in water. They try to escape into the atmosphere. And so it actually has everything to do again with the polarity of the molecule, whether they dissolve in water or not. All right, so that's solubility. At this point of solubility, all you got to know is to compare polar, nonpolar, ionic to tell me if it dissolves in water. So what does not dissolve in water? Oh, the other thing I should point out, non-polar compounds, but also, if you take a block of metal and you put it in water, it will not dissolve. Yes, it sounds funny, but like, it should be said. Pure metals do not dissolve in water. You agree? So if I say I got copper and I put it in water, is it going to dissolve? It's just going to chill, like chilling. If you got aluminum, you put it in water, think of aluminum foil. Throw it in some water. Did it dissolve? It did not. You can do that on your own at home. There's some metal in water. It won't dissolve. Now, are there metals that can react in water? Yes, and we will explore that in the next unit. But right now, we're just talking about dissolving. Some explode in water, yes. I said explore, but explode also counts. Yes. Yes, it does. All right. Next thing is called electrical conductivity. There are a couple things you need to know about electricity in this class. I know electricity itself is a physics thing, but if you'll recall, chemistry crosses into both physics and biology. So here's what you need to know about electricity. Electricity is defined as the flow of electrons. So electricity is the flow of electrons. So the guiding principle on whether or not something's going to conduct electricity is if you have electrons that can move. If you have electrons that can move, yes. If they cannot move, no. So with ionic compounds, in order for electrons to move, it's got to be aqueous. What does that mean? Molten or aqueous? Molten means, think of molten lava. What does that mean? If something's molten lava cake? Molten? You ever heard of magma, like coming out of a volcano? What is that? Liquid. So if you can take an ionic compound and change it from a solid to a liquid, then it will conduct electricity. Ionic compounds in the solid form are stuck in place. They will not conduct electricity. The ions are stuck in place. So molten means to melt it. It has to be in the liquid form. If it's in the solid form, it's not going to conduct electricity. That's dangerous. Like hundreds and hundreds of degrees.
Is this connected to superconductors?
A little, yeah. Aqueous means what?
Dissolved in liquid?
Dissolved in
Water.
water. So what happens when you take an ionic compound like Na plus and Cl minus and you dissolve it in water is you separate the ions from each other and they can move through the water. And so in order to conduct electricity, you need a flow of electrons. The only way that electrons can flow is if electrons can move. And so either that's going to happen with ionic compounds if you melt it, not in the solid phase, because in the solid phase the particles are stuck. You have to either melt it or dissolve it in water to get it to conduct electricity. Pure metals always conduct electricity. So pure metals always conduct electricity. They conduct electricity in the solid form. And we're about to go into why, because that's the beginning of the second part of the notes, the one that says Unit 2, Part 6, IMF continued. But pure metals always conduct electricity. Think about it. Copper, what your electric wires are made of, they always conduct electricity. All right, here we go. Remember to stop at 1:45. Or we stop at 1:45 is where we stop. And we have to finish next class. Yes?
Pardon the interruption.
Yes? Yes?
Stephen Davis is going home.
Alrighty.
Thank you.
All right, this is the, so you don't forget it. The group project, remember to have them on dial. So you can make a decision. You got to make it quick once it's time. So have Steven in a text or something. When it's time, yeah. You'll find out shortly. All right, so covalent compounds, current slide. Do they ever conduct electricity? They do not have free electrons. Covalent compounds, the electrons are stuck in covalent bonds. So that's why in earlier science class you were told that they were insulators, or that nonmetals were insulators. They were not conductive. So the idea is that if you've got something like, I don't know, CH3OH, all of these electrons are stuck in the electron cloud together. There is no transfer of electrons taking place, no movement of electrons equals no electricity. Bye. Have a nice weekend. No movement of electrons equals no electricity. Covalent compounds have no movement of electrons, no overall movement. They're stuck in place, held bound to the elements in the compound is the way to understand it. So then, have you been told that water conducts electricity? So why? Water's covalent. Let's talk about it. Does distilled water conduct electricity? It doesn't. So distilled water, which is pure water, does not conduct electricity. So why have you been told that water conducts electricity? Because tap water, or whatever is coming out of, your sinks, has ions in it, right? Tap water has ions, like sulfur or chlorine or fluorine or calcium or magnesium in it. And those ions are the ones that are flowing because they have charges, and those ions are what's conducting the electricity. So because they are aqueous, AQ in parentheses means aqueous, means dissolved in water. They conduct electricity. So does actual water conduct electricity itself? No, it's what's in the water. It's the ions in the water that's conducting the electricity. So if you have pure water, if you have distilled water, it does not conduct electricity. Purified water has ions in it. Purified water has ions in it. Spring water has ions in it. The only water that is not supposed to have ions in it is distilled. Yes.
What is distilled?
It's an actual physical process where they boil water into a second container. So the water that has the impurities stay behind and the water itself gets boiled out. Because the impurities, can you drink it? Absolutely. The ions are actually healthier typically because we need ions in our body. So if you drink too much distilled water, like at too much volume of it, it actually dilutes your system. Yes.
Yeah, I was about to say that.
Yeah, you shouldn't have a ton of distilled water, but you can have some. Yes. Yes. Justin. Yes. Because the ionic compounds don't boil at as low of a temperature, so the ionic compound will be left behind. So it would leave like salt behind. You can actually do that by boiling salt water. You can boil all the water out and you leave the salt behind at the bottom. Exactly. That's evaporation. That's exciting, I guess. You can. Distillation works for alcohol as well. All right, we're going to go ahead and continue. Electrical conductivity. So let's answer a couple more questions from the textbook, then we're going to continue. Aluminum oxide has a melting point of 3,000, but aluminum chloride changes to a vapor at 178. What's happening? And I'm just going to be quick here. And this is actually kind of rude, but Remember aluminum chloride, y'all? So this is aluminum chloride. Aluminum oxide is this. What's the difference? Aluminum chloride is. Aluminum oxide is. Rude. It's rude. Why is aluminum oxide ionic? Because the difference in electronegativity is 2. The difference in electronegativity between aluminum and chlorine is 1.5. 1.5 falls into polar, covalent bonds. 2.0 falls into ionic. Is something you're supposed to memorize. So you may just want to commit to memory these specific 2 compounds because they are tested by Cambridge. They'll give you aluminum chloride, they'll give you aluminum oxide, and they'll ask you to compare them. You don't have to memorize the numbers, but I would memorize the compounds. That aluminum chloride is covalent and aluminum oxide is ionic. I would just memorize that because they like to compare these 2. This is from the Cambridge textbook. Now, aluminum chloride is covalent. Because it's covalent, it's going to have a low melting point and boiling point because why? AlCl3 is held together by much weaker forces. Yeah. Then Al2O3. And then what are the weak forces? It would be dispersion. And then for Al plus 3O minus 2, what is the actual forces that holds that together? It's actually ionic, right? Ionic is an intramolecular force, so it's much stronger than an intermolecular force. So that's why. And then magnesium chloride conducts electricity when molten, but not when solid. Why? It's an ionic compound. An ionic compound does not have free electrons to move unless it is molten or dissolved in water. So an ionic compound must be molten in order for electrons to move. And electrons have to move in order for there to be electricity conducted. If electrons don't move, electricity can't be conducted. So in the solid phase, the ions are stuck in place. The electrons cannot move. So they have to be molten or aqueous. In this case, it's molten, but not solid. So when you melt it, the electrons will be able to move. So this is, yes, almost done. Looking at what we have left. There's some repeat slides in here in the second part, FYI. I just realized there's repeats though. 2 pages of repeats. So don't stress too much. And I'll explain what alterations will get made if we're not done by 1:45. All right, iron conducts electricity when solid, but the ionic solid iron 2 chloride does not conduct electricity when solid. Why? All you gotta say is iron is a pure metal. Whereas iron 2 chloride is ionic. Remember, metal and non-metal is ionic. Then the last one here, sodium sulfate dissolves in water, but pure sulfur does not. Sodium sulfate dissolves in water, but sulfur does not. do you think? Sodium sulfate, what's that? I'm gonna write it. What type of compound is that? Ionic. That's the decision you have to make. Ionic. What is pure sulfur? Anybody remember? It's actually S8. I have not re-asked you to memorize the standard states yet, but that's coming in Unit 3. Regardless, this is a pure element, right? And this is an ionic compound. Why won't sulfur dissolve in water? It's the same element connected to itself 8 times. Is it polar or non-polar? So it'll be non-polar, right? So S8 is non-polar. So it will not dissolve in water. Non-polar is covalent. So it will not dissolve in water. And what about sodium sulfate? Whereas Na2SO4 is ionic and will dissolve in water. Alright, so before we talk about your project at 1:45 and you get to work on bending water as a team, we still have a couple of things to touch base on. We're going to the second part of the notes that I passed out. In the second part of the notes, you could actually cross out slides 8 through 15. We just did those. We did 8, 9, 10, 11, 12, 13, 14, 15. I accidentally double copied them. 8, 9, 10, 11, 12, 13, 14, 15. So this is actually a lot less than you think it is. Yes. Sure. On the bottom it's labeled. 8, 9, 10, 11, 12, 13, 14, 15. You're welcome. 8 through 15. 8, 9, 10, 11, 12, 13, 14. We just did those, actually. So I'm going to go ahead and keep this and move to the other part. Well, actually, 3. We got to do 3, right?
Yeah.
So this is continued. We're not going to finish all of this today. We're not going to get to, I don't think we're going to get to graphite and diamonds today. I think we'll be doing that next class. But we are going to talk about metallic bonding. We have to talk about metallic bonding before we do. So, Unit 2, Part 6, IMF continued, structures. Here we go. Learning objectives. What we have not done yet that we need to cover is metallic bonding. The other part that talks about structure is going to require more, it's going to necessitate more time, and I don't like to rush, if that makes sense. So I am going to make a few adjustments. I'll tell you what they are at 1:45. We are still going to go over your project today. We're going to try to bend some water. We're going to do that for sure. I'll tell you a little bit of adjustments and due dates. You'll notice I posted your paper 1 questions. I did post them last night. We'll talk about that in a little bit. But learning objectives, here we go. You are going to today go over metallic bonding. We've also already went over hydrogen bonding. This has been done. And we have talked about some of the effects of hydrogen bonding. So that's done. I think I'm not going to have enough time to go over this because it's too big of a topic. So we will get to that next class. I don't want to rush it because it's something that a lot of questions are asked about by Cambridge. So here we go. Let's get to metallic bonding. Thankfully, I organized your homework where everything we covered today should be in your homework. I'll double check it, but your homework should be on just what we have covered today. I'll double check though before we go. Metallic bonding. In pure metals, there's a new type of bond you need to be aware of. So on the top here, write types of bonds. We learned covalent. We metallic is no. So covalent is the type of bonding between what type of elements? Between atoms of nonmetals, right? Or, there's an or, right? Because why is aluminum chlorine covalent? Between atoms of nonmetals or elements with close enough electronegativity to each other, right? So, or elements with close enough En to each other. So covalence is a little bit more complicated than it's initially presented in previous class. Because it's definitely nonmetals, but also includes some exceptions if you have a metal that has a high electronegativity. Second type that we learned of type of bonding is called ionic. So in ionic bonding, this is a metal and a nonmetal, or an electronegativity difference of 2.0 plus. So that's what we call ionic bonding. A compound will have ionic bonds if you have a metal and a nonmetal, or the electronegativity difference is 2 or above. And now here we go. The new type of bonding is for pure metals. They have a different type of bonding. They don't share electrons. They don't transfer electrons. Something else is happening. And so the last type is called metallic. And this is for pure metals. So pure metals, and then I'm going to explain what you need to know about metallic bonding. So if I have just copper, or just gold, or just silver, some kind of pure metal from the periodic table, it has its own type of bonding. It is not a compound. But if you have gold, it sticks together, doesn't it? Gold is in the solid phase. If I have iron, it sticks together. It's in the solid phase. So electrons aren't being transferred. Something else is happening at the atomic level that you have to understand. So this is what it is. When you have a pure metal, meaning you've got a bunch of that element, billions and billions. I don't know what 10 to the 23rd power is, like in words. Remember Avogadro's number, 6.02 times 10 to the 23rd? That
No,
thing?
7 is a million.
It's a lot. You got billions and billions and billions of atoms, right? And if you've got 6.02 times 10 to the 23rd gold, it's like half a pound of gold. So it's a pretty good amount of gold. But you've got a lot of it, let's say. The nuclei, what's nuclei again? Plural of nucleus. So it's the protons in the nucleus. The nucleus and the electrons actually become delocalized. What does that mean? If you have a pure sheet metal, the electrons stay between the nuclei of the separate atoms, meaning that if electricity was applied to a pure metal, because the electrons are not completely bound to the nucleus, they are stuck in between the nucleus of separate atoms, those electrons can move. We call this a sea of electrons. And so the way to understand it is that metals that are in a lattice, their electrons and their valence electrons specifically stay in between the different nuclei of the metal. And they exist in what's called a sea of electrons. Sea, like, you know, the ocean. Like an ocean of electrons. And any electrons that exist in the sea of electrons, so we call this the sea of electrons. And that is used by Cambridge, a sea of electrons. And so if you've got metallic bonding, you've got a sea of electrons And these electrons are free to move. Because they are not completely attached to the nucleus of any single atom anymore. They're delocalized. They're detached is a way to think of it from the nuclei. And so the way to think of it is that the nuclei are still positively charged because remember protons are in the nucleus and the electrons are floating in between the nuclei of separate metal atoms. And so that's what delocalized electrons mean. You are potentially going to be asked, so this means memorize. Write it on your notes. You are potentially going to be asked the definition word for word for metallic bonding. And its official definition is it's the electrostatic attraction. What does electrostatic mean? Electric attraction. So positives and negatives again, right? So metallic bonding is the attraction between the positive ions of the nucleus of each metal and the electrons that are close by. We call those the delocalized electrons. And so it is the attraction between the positive metal and the negative electrons. Do you think this is a strong attraction? You've got a fully positive nucleus, right? And you've got fully negative electrons. Do you expect this to be a strong attraction? It's definitely strong because they're fully charged. Because fully charged, which is why almost every metal on the periodic table is a, because it's a very strong attraction. Hey, you gotta look at Mercury. Mercury's weird. Once you get to heavy metals, things get strange. Once you get into transition metals, things get really strange. We don't talk about transition metals in AS chemistry. It's kind of like we don't talk about Bruno if you watch that movie. We don't talk about transition metals in AS level chemistry. Like we barely talk about them. Every once in a while it's mentioned, but they're strange. So we leave them for A level. There's a whole like unit test on that, on transition metals. But it's not tested in AS for the most part, except for like that, except for the copper and chromium. All right. So what can you be asked to do? You could be asked to literally draw this. And I believe I put one in your homework that you are asked to show metallic bonding. So if you are asked to show a diagram of metallic bonding, you would need to draw the positive nuclei of the separate metals and the negative electrons in the sea of electrons. And so if you have a group 1 metal, it would be a +1 charge. If you have a group 2 metal, it would be a +2 charge. And how many valence electrons would be floating for the sea for each atom? 2. And so it would be a 1-to-2 ratio. So if they ask you to draw, this is what they're expecting to see. Strength is affected, and yes, you can be asked for this. Strength can be affected by how positive the charge is. So that means that a +2 charge is stronger than a +1 charge. The smaller the size of the metal, the stronger the bonding. And the greater the number of mobile electrons, which are specifically the valence electrons, the stronger the bonding. Now, I know that I'm about to end with this topic, but this tends to be something that students don't remember to study. Because there's very few questions, but there are some questions about this that can show up. They're very infrequent that it shows up, but it does show up. You need to go study this. I want to bring up, what do we mean by strong? What does that mean? Metallic bonding is strong. What do we mean by that?
Takes a lot of energy to separate them.
So it means high force of attraction. And the higher the force of attraction, the higher the what?
Boiling point?
Right. So that means the higher the positive charge, the higher the boiling point. The higher the number of mobile valence electrons, the higher the boiling point. The smaller the size, the higher the boiling point. So what we're talking about here, high force of attraction, means that this affects melting point ends So it's boiling point and melting point. I'm just bringing this up. I think I tried to insert a couple questions about comparisons, but you should have this down. This is where we're going to end today so that we can go over your project. What we have left to do before we end the unit. We have to go over different types of structures, and we have to go over the gas phase. So I will give you an update next class, but I believe your test date's not going to change because I already pushed it back one day. But I am going to give you some extra time on the project from what it says on the screen. So because I haven't finished structures yet, you can't really answer those questions. So let's talk about your project, and then you're going to get in groups of 3 for the first activity you're going to do as a group. It's going to be Wednesday, October 4th. So it's still 2 weeks from now. A little bit less than 2 weeks from now. So we're going to stop here. I'm going to explain your project. Aha. And it should be also, yeah, group's already made. All right, I'm going to talk about what it is first. Then have Stefan on text ready, because you're going to have to make a choice. But I'm going to first talk about your project. What? Did you say steal information?
You got an iPhone, right?
I do have an iPhone. Oh no, stay away from my iPhone. Anyway, here we go. So what I'm going to be changing, just to be clear, is when your project's due, it's gonna, instead of being due next Wednesday, because I'm taking a little bit more time to go over what needs to be went over. It's gonna be due instead of Wednesday, it's gonna be due next week on Sunday. Which means on Monday, the day before the exam, you would be doing your presentations. So you will be doing presentations on this project. That is going to be a component. And so I will fix this and I'll repost it online shortly. It should auto post with this date, but you'll see that I'm going to fix it. So here we go. Here's what you got to do. Instead of presentations taking place on Thursday to give me a little bit more time to finish the information, it's going to take place on Monday. Monday, which is the day before the exam. So Monday, October 2nd. Here's what you're going to have to do. Part 1, make a 10-slide Google slide presentation based off your answers to the questions below. You're going to be given a choice, and it's going to be randomly assigned which team gets to choose first. One of you are going to be given a medal, a pure medal. One of your teams is going to be given a covalent compound. One of your teams is going to be given an ionic compound. And then some of the special types of compounds we're going to talk about next class, which is why I said you need a little bit more time. That'll be in there as well. You'll see what the choices are shortly. But each of your members, you're going to have 3 people. We have 18 in this class, so it works out perfectly this year. 3 people. One person is going to be in charge, and you have to decide who and let me know who's doing what so that your grade is dependent on that. Person number 1 is going to design your 10-slide presentation. Person number 2 is going to be your artist, meaning that they're going to be drawing the structure of whatever that compound or metal or molecule is. So in your group of 3, you got to decide who's your best designer. And then group member number 3 is your game specialist, meaning they're going to create either a 20-question Kahoot or a 20-question quizzes or a 20-question gym kit at least, and we're going to play those on Monday after each of your presentations. So we're actually going to play each of the games you make, okay, to practice, to review. And so this is actually something I like to do to review this intermolecular forces topic. You'll see there's a bunch of questions in here to answer, but that doesn't make any sense until you know what you're assigned. And so let's take a look at our groups. So I do have the groups here. I have group 1. Take a look, it's on the screen now. If you're looking at the screen, it's also up on the screen in the front. Group 2, group 3, group 4, group 5, and group 6. So I tried to take into consideration if you had a request, but not everybody had specific requests. So I just did the best I could with what I had. But you do have to be 3 people per group, and this is the group for this project. If you have something you want to change for the next project, you can email me, but this is the group for this project. You will need each other's contact information before you leave today. If there's a member in your group you don't already have the contact information for, so you can work together. You will have the ability to work together very shortly because I'm going to ask you to try to bend some water, right? So you'll be working as a group in that shortly. But let's talk about what's going to happen. So one group is going to choose graphite, or if it meets your fancy, another giant molecular structure of your choice. If you look at the Unit 2 Part 6 notes and you make that choice, you'll see that the choices are graphite or diamond or silicon dioxide, which makes glass, by the way. And the last one would be carbon nanotubes, if you're interested in that. So that's one group. Another group is going to be actually given carbon nanotubes to study. Another group is going to be given magnesium, or if you have a fancy or preference for different metal you would like to study, it has to be a pure metal. So you could study gold, you could study sodium, and then you'll see in the project requirements what you have to answer about that. Propan-2-ol. Anybody know what that is? It's an alcohol. It's isopropyl alcohol, rubbing alcohol. Fructose is the sugar in high fructose corn syrup, right? And sodium chloride, so you see these ones that don't have a choice, you have to do that one. So if you pick fructose, you have fructose. You don't get to pick glucose, you have fructose. So that's the one you have been assigned. And then the last choice is sodium chloride, which is salt. Or if you want to be extra salty, you can pick another ionic compound if you don't want to work with regular table salt. And so these are the groups, group 1 through 6. I'm about to pick up a wheel. So here's what's going to happen. To be as fair as possible, I'm going to spin the wheel. Group gets called, going to decide what they want first. Then the next group decides, then the next group decides, and the last group doesn't get to decide. But the last becomes first the next time. So next time there's a group project, the last group gets the first decision. That's the way that I like to do it. So here we go. Here's a wheel. So I'm going to pick up the spinner. I'm switching it to numbers.
No, 4.
What's
the next thing
What?
We're group 4. Yeah, I was right there.
All right, here we go. Your groups, I will tell you, if you get called, you make a choice, I'll write it in. Ready? Here we go. First group to choose is group 6. That's Damani, Melina, and Kat. You have a minute to decide. Your choices are graphite or some other giant molecular, carbon nanotubes, magnesium, propan-2-ol, fructose, or sodium chloride. Fructose? Alrighty. So group 6 has taken fructose. Who's your art designer? You've given them some work. Because fructose is a little bit big, right? It's a biological molecule. All right. Next up. And by the way, if 6 gets called again, I'm just going to spin it, okay? All right, so fructose is out. Bye, fructose. Next group. Group 4. He's right next to you. Decide between you. You have a minute to choose. What you want that you haven't already been chosen.
Sodium chloride.
What exactly are our options?
What's left? Graphite, carbon nanotubes, magnesium, propan-2-ol, and sodium chloride. Yes. Peter's right there. Wave your hand, Peter.
I think sodium.
All right, so you said sodium? Sodium chloride or sodium? Sodium chloride or pure sodium?
Pure sodium.
Pure sodium, so that's taking a pure metal off the board. All right, so you've got metallic bonding, just so you're aware. That was group 4. So, sodium, which is pure metal. So pure metal and fructose is off the board. Group 2 is next. So, get Stefan on the line. I mean, it's up to you. It's your friend. Are you going to choose without him? The choices are graphite, nanotube, propanol, or sodium chloride. You can pick diamonds. You want to check with him first? Okay. Remember, we're going to go over diamond next class. We will go over each thing. Explosive kit. Are you the designer?
I have no idea. You already have it. Hold on, I'm gonna add it. I won't be stopped. 22.
Yeah. Do you agree? Okay. So we will go over diamond next class. If it's a material I haven't yet explicitly reviewed, it will be done next class. All right, next group. We still have 3 groups left to decide before we get to what we have to do next. Group 3, Diane, Ernesto, and Rosalind. Ernesto, they thought carbon nanotubes. All right, carbon nanotubes.
What's left?
So what's left is the alcohol and the ionic compound. The alcohol and the ionic compound. We have 2 groups left. So the choices are between alcohol and a salt. I'm looking for group 1 or 5. So 1 or 5.
Wait, what about 8?
5. So David and Peter, between the 2 of you, salt or alcohol? You're going to take the organic? All right, alcohol. Here we go. Which means group 1, you don't have a choice today. Which means you are first next time. You are first next time. So that means you have, do you have a preference of ionic compound, or would you like to go with the classic table salt? Do you have another ionic compound that meets your fancy, that you prefer? You have a minute to decide. Got a good feeling about any other type of, you want to go with classic table salt? Okay, classic salt. Maybe you're a little salty because you got picked last. Anyway, you will pick first next time. I'm writing that note. Pick first next time when I post it. All right, so you've got your group ideas of what you need to do. Remember, I am fixing the due date. Instead of making it due next Wednesday, I'm making it due on Sunday of next week. You have to have it done in time because you got to present the next day. So late work is not a thing. You will be, if you don't have it, you don't have it. We're going to know you don't have it. So make sure you have it in on time so that you get the grade for it. Remember, 3 members, 3 responsibilities. 1 person's in charge of the presentation. 1 person's in charge of designing the molecule. 1 person's in charge of the game for your team. So you'll get to talk with your team members and decide. So before we leave for the day, I said we would do a couple things. First off, let me hand you the homework before I forget. You don't want to forget that. So, in terms of homework, let me just make sure that everything has been covered. Everything has been covered that's in the homework. Yep. I just wanted to double check. Everything in the homework I have already covered. So I'm passing out the homework first. Then we're going to move to the back, but wait till I tell you, okay? I got to get it ready. Here you go. Here you go. Here you go. All right, so let me show you what you're going to attempt today with your group. So there's going to be 6 groups. You'll get together with your group. Let me tell you or show you what you're going to try to do today. So I'm going to YouTube to show you. See if you can do it. I'm going to YouTube to show you what it is you're going to attempt to do. My lab aides were able to do it last week. They proved that it could be done. So you're going to see if you can do it as well. What? To not do it or do it? All right. I'm sorry?
Are you really stressed? You're on a deadline.
Oh, to bend water?
No, just like music, like classical music.
Yeah. All right. So I'm just going to show you real quick what it is you're going to try to do. It's not going to look exactly like this. I'll show you what yours looks like, but just so you can see. I'm going to turn my microphone off